Hello, my name is David Brochart and I currently work at Quantstack, and this presentation is about collaborative editing in Jupyter. So you will probably see very often the three letters RTC, and they stand for real-time collaboration. And what we mean by that is the ability to work on the same document at the same time and see changes live. So with Jupyter without RTC, you probably have seen this pop-up window that appears when two users work on the same document, basically making it impossible to do so. But in JupyterLab with RTC, you can have multiple windows connected to the same server. In this case, it's using WebSockets, and it also works in JupyterLite. In this case, users are connected peer-to-peer using WebRTC. So you can go to these two URLs.
Either this short one or this one, https://davidbrochart.github.io/jupyter-shared-drive. And there is a JupyterLab instance, JupyterLite instance there that has collaboration enabled. So if you go to this, this drive there, you could actually, during this talk, work on the same document. So for people who have a laptop or even a smartphone. But maybe I will show that at the end of this talk if we have time. So collaboration in Jupyter is using what we call CRDTs, which are basically data structures with superpowers. So CRDT stands for concurrently replicated data type. It's kind of complicated, but let's look at each of these words. Data type means either some text or some array or some map. In Python, this would translate to this str for strings, list, or dict. Replicated because the data doesn't live in a central place, but it's distributed. Each client owns the data, and concurrently because the data can be changed at the same time on different machines. And changes are made on all the copies of the data that live in each client, and CRDTs have a special algorithm that ensure that the document state stays the same on every client. So when we make changes to this kind of data types, the changes can be observed. So we can register a callback that will be called with the event describing the changes. The changes can also be serialized to binary, which allows us to send them over the wire using either WebSocket or WebRTC or any other technology, and it can be applied on the other end of the wire to a remote user. But to the end user, CRDTs are actually a very simple kind of data because you just create a shared object like a text. You connect it through a provider, which is using WebSocket or WebRTC. You react to changes because you observe the changes on the data. And you can actually see these kind of data structures as log-free shared data. So it's kind of multi-threading without the issues of using logs and semaphores and so on. Do we need actually CRDTs? Maybe we are not convinced. But let's look at this simple example. We start with two users who work on the same shared document, starting with a blank page. So let's imagine a text editor. One user types A, the other user types B at the very same time. So the event is insert A at index 0 for user A. For user B, it's insert B at index 0. Before the changes propagate, user A sees A on his screen. User B sees B. After the changes propagates, user A sees BA. and the other one sees AB. So the documents have actually diverged, and we are not collaborating on the same document anymore. You can look at this slide slowly at home and convince yourself that it's actually the case. But we could also say, can we use another technology? We could use a centralized architecture and have users access the same document which is hosted on a central place. So users would, for example, post the changes they want to the server and listen to the actually applied changes back from the server. So user A could post insert A at index 0, B insert B at index 0. And when they hear the reply back, they would both see insert A at index 0, insert B at index 0, and they would both have BA at the end of the day. So that works. It's not using CRDT, but it's got some issues like latency, because you need to wait for the reply back from the server in order to see what you are going to show on the screen, for example. So there is some latency there. And also, what if connection breaks? What if you are working offline? And what if there is no server? What if you're on a distributed architecture, like in JupyterLite, for example? CRDTs allow to do all of these things. But they are really a paradigm shift. You really have to think differently when you work with them. So we often talk about local first applications. Now the application owns the data. There is no latency. Once you make a change to a data, you can reflect it back on the UI, for example, and data is synced in the background for you. It's completely transparent. Your application just needs to react to data changes that are coming from the outside world. And you can still use the server, of course, if you need to access some data that is remote, but it's not mandatory. You can work offline, and you can reconnect later, and it's all going to sync magically. So the application is not a master anymore sending requests to a server. It's more like a slave receiving changes and updating accordingly. In JupyterLab, we have the following libraries. In the front end, YJS, which is a JavaScript implementation of CRDTs, a very popular one, maybe the most popular one. JupyterYDoc uses YJS and creates structure for the kind of documents we use in the Jupyter ecosystem, like a text or a notebook. And we have the Jupyter collaboration library, which is using WebSocket. So JupyterLab, your browser connects to the server using WebSocket. In the backend, we have PyCRDT, which is Python bindings for wires. We call it wires, wire RS, because it's written in Rust. And it's the Rust port of YJS. We also have the equivalent of JupyterYDoc, which represent these shared documents. And the backend part of Jupyter collaboration, so it's a WebSocket server. We have the notion of rooms where users share a document. And some features are implemented, like auto-saving and out-of-band changes when files are changed, for example, using the terminal, but not really through the notebook editor, for example. So that's taken care of also. We have CRDTs in JupyterLite. That's quite new. The difference in JupyterLite is that there is no backend. In the front end, we still use YJS as before, JupyterYDoc, and this new library called Jupyter Shared Drive, which is kind of the equivalent of Jupyter collaboration, but using WebRTC instead of WebSocket. So WebRTC connects the browsers between themselves, peer-to-peer, instead of through a centralized architecture. So the drive in Jupyter Shared Drive doesn't replace the default drive as it's the case for Jupyter collaboration. You can think of it as a scratch disk when you import files from the default drive. So as I said, the architecture is distributed. The file system itself is a shared document, and each browser has a copy of the files. So the files are kind of ephemeral, actually. If all clients disconnect, documents won't exist anywhere. There won't be any more reference to the file, and you will actually lose your data. So you have to export it back to the default drive. So what do we have for free also with CRDTs? We have an undo manager, which allows to undo and redo changes. That's what we use in a new library, in a new feature in Jupyter Collaboration, which is a document timeline. So you can go back in time using a slider. I'll make a demo of that. There is Git-like operations, like you can fork a document, and that allows us to implement a suggesting system that I will also demonstrate, sorry. And it also brings a kind of unified architecture with the ability to model almost any kind of data because it's JSON-like. And as I said, it's very easy to connect through providers, WebSocket or WebRTC providers. For example, we can think of a system, a chat system that would, where users could talk to an LLM agent that could modify the notebook, for example. This is not actually a dream. This is being implemented right now in Jupyter AI. That's a demonstration of the document timeline using the undo-redo manager. So I can create a notebook, move this slider, go back in time, redo the changes, undo the changes, revert to a special state in history. So that's quite new. It's actually in a pre-release of Jupyter Collaboration. We have a chat system using CRDTs. You can already install it. It's Jupyter Chat. So I create a chat on the user on the left side, on the right side. I type a message received on the left side. Just a regular chat, but still quite nice. So let's see if I can make a demo of the suggesting system. So let me see if I can bring this window here. Yeah, okay. Here I have two I'm not seeing very well here. Okay, that seems to work. Come on. So here, let's open this notebook. Why is it? Taking so much space. Let's remove this one. Let's open this notebook here. So here, we are indeed collaborating. And now here I have this menu. where I can, I'm in editing mode, and I'm going to switch to suggesting. So here I'm informed that my edits now become suggestions. On this user, I'm notified about a new suggestion. I'm asked if I want to view it. Let's not view it right now. So here I am suggesting, and I don't see the suggestion here because I chose not to follow it, but I can change my mind later. So the UI is not very polished. I have to choose here the ID of the suggestion that will be improved in the future. And now I see the change that I made in the other window. And, and I can also actually collaborate on the suggestion as well. And in the end, I can review the suggestion and choose to discard it or merge it back into the root document. Here I merge it, and I'm back directly editing the document. So of course, the UI is not very nice. We are going to improve that and offer a Google Docs-like experience in the future where we would have on a unified view all the suggestions displayed by all the users. That's the goal. Okay, let's go back here. Now I want to demo cross-platform interoperability. For example, a browser talking to a terminal through collaboration. All right. So what I'm going to do, I'm going to launch JupyterLab. I'm going to copy this URL here. All right, so that's just JupyterLite as we know it. And now I'm going to launch Jupyter, which is a terminal-based Jupyter client that is going to access the same server and it is also using collaboration. So let's see if we can collaborate between a terminal and a browser. Let's open the same notebook. Yeah, it works. Oh, let's execute. So I think that's cool because that really demonstrates that CRDTs are a kind of universal technology that can really connect anything as long as you can send the updates on the wire. So there is also some new features that are enabled by collaboration in Jupyter. One of them is server-side execution. So when we use JupyterLab today, server-side execution is not enabled. So basically what we do is let the front-end speaks the kernel protocol, which is a very low-level and complicated protocol. So the kernel sends execution request to the backend talks to the kernel, sends the reply back to the front end, which has to interpret it and change the notebook accordingly with the outputs that were provided. And then that goes back to the front end and then back to all the front ends. So it's kind of complicated. The diagram looks like that. So we have an execution request coming from the front end, forwarded back by the backend to the kernel. The reply goes through the backend again to the front end, does some processing, updates the outputs, goes to the backend, and back again to the front end. So it's not the best kind of architecture. With server-side execution, we don't forward the kernel protocol to the front end. Instead, the front end just sends high-level requests like execute this cell, and the backend takes care of all the communication with the kernel. So the kernel executes the code, sends the output back to the backend. The backend updates the notebook it has, because it has a representation of the notebook internally. And then that is automatically synced through CRDTs to all the front ends. So the front end is really, the front end's job is really simplified in this case. It becomes merely a notebook editor that has to react to changes. If we look at the diagram, it's much more streamlined. We have the execution request, intercept by the backend, that talks to the kernel, gets the reply back, populates the notebook, and outputs are magically updated to the front end. There is a new implementation of the Jupyter server, which is called Jupyverse, that supports this mode of execution. The good thing about that is that there is no need to keep a browser open during the execution. You can close your browser once you execute a cell, for example, let's say a long-running cell. Execution happens on the back end, and if you reconnect, you will get back all the outputs of your execution, which is kind of nice, and it has actually been a very long issue for a very long time in Jupyter. So that's basically solved now, but it works for simple static outputs, like maybe images or text, but not for dynamic outputs. And when I mean dynamic, I'm talking about widgets. So what would we have to do to make that work with widgets? We would have to make them collaborative. Currently, IPyWidgets, which is the foundation of Jupyter widgets in the Python world, actually, is kind of collaborative. So you have all these sliders, checkboxes, different kind of UIs, simple UIs or more complex UIs like IPyLeaflet for maps, IPyDataGrid for data grid representation. It can work with multiple clients, but it's not fully collaborative, so there is no conflict resolution like with CRDTs. The widget models live in the kernel and in the front end. Both are kept in sync, but you cannot, for example, restore the state of the widget if you disconnect your front end. We have a new implementation which is kind of ironically called YPyWidgets because it's using YJS. That would allow to do that. The idea is basically to generalize the idea of shared documents that we implemented for texts and notebooks to widgets. So it would have a conflict resolution, and you would be able to reconnect and have your widget state restored with that. There are two projects which use YPyWidgets. They were presented just before this talk. One is JupyterCAD, the other one is JupyterJS, so I won't talk too much about that. The future of CRDTs, actually, YJS is already used in the core code base of JupyterLab, but we indirectly use it through a wrapper observable package. YJS is more powerful than observable, so the question is, there is the question of getting rid of this wrapper and using YJS directly in JupyterLab. That's something we are discussing. So the two collaborative systems we have today are Jupyter Collaboration with a centralized architecture and Jupyter Shared Drive for distributed architecture. CRDTs are really defining the Jupyter architecture because of the API, which is changing according to that. For example, the file system API in JupyterLab is changing with the use of CRDTs, and we could actually do the same for the kernel API. Why not imagine a shared model for kernels? And as I said, CRDTs are a very good fit for JupyterLite because it's a distributed architecture, and you can expect to see more of that in the future. So with that, I thank you for your attention.
So thank you, David. So we have time for one quick questions. Yeah, okay.
Hi, thank you for the great talk. Why did you choose YJS compared to, for instance, AutoMerge, which is the other contender in the CRDT space?
Yeah, so AutoMerge was one of the options. At the time we chose YJS, there was a project in the Jupyter ecosystem that evaluated this solution. It was not very conclusive, and basically there was kind of competition between AutoMerge and YJS, and we chose YJS because it worked and AutoMerge didn't work at the time. So I heard that they made very good progress in them since then. But still, when I look at YJS, I think it's more mature, much more popular. I don't think they have Python bindings for AutoMerge yet. They have a Rust implementation, but no Python bindings, and it's much more in beta, let's say. I don't see it as production ready yet. I might be wrong. I know other CRDTs, I've heard good things about Loro, but I mean, they all have their pros and cons. Loro might be more performant, but it's really, you know, benchmark are very subjective, so we are very happy with YJS. The developers are very reactive, so yeah, I think it's a good choice.
Okay, thank you. So we can again thanks David.
Thank you.